Okay, so yeah, we just stop here, and then here we talk about the Gauss law applying on the planar symmetric. So last hour we have covered a similar case, but for that case it is a conductor. But here we have a non-conducting plate. So it is, we assume it is thin. It is thin. So this is not drawing very nice. So if I draw it, it will be something like this, which specify it is very thin. Thin, infinitely large, and non-conducting. Non-conducting is very important here. So with a uniform positive charge surface density, sigma. So we have a charge density. So just now someone has asked me the charge density. We have linear charge density and then surface charge density. They have different SI units, and you can check back in chapter 22. They share the same notation. And yeah, so we can apply the Gauss law similar to the previous case. And we define the Gauss surface like this. And in this case, as long as it is thin, so it will generate E field on both left side and right side. So for the integration part here, we have this side should be EA and this side is also EA, so that we have 2 EA. And then for Q enclosed, it should be this A multiplied by the surface charge density. So it is a total charge. So A and A can be cancelled. So now we have this factor of 2 here. So we have this factor of 2 here. So this is actually this case. So we can use different ways to get the same conclusion. If you don't know the Gauss law, you can use the E field, and then you try to write out the dE, and then you do the integration. But as long as we have learned the Gauss law, so we can only use 1 step, 2 steps, and 3 steps, and then we come up with actually the same conclusion. So next, if we have more than one planar plate, 2 conducting plate here, if we have 2 conducting plate here, what will it look like? So here, suppose we have this one first. You just ignore this one first. So we have a conducting plate with a positive charge. So the charge will be distributed on the surface, not inside. So half of the charge will be on the left side, half of the charge will be on the right side. And this is infinitely large, so that it goes to infinity. So that there are no charge on the top and bottom. And here we assume the charge density is sigma 1 on both sides. On both sides. And in this case, E plus will be sigma 1 over 2 epsilon naught. Sigma 1 over 2 epsilon naught. Yeah. And here, if we have a negative charge with the same charge density, so E minus will be sigma 1 over 2 epsilon naught on both sides. So if we place these 2 plates close together, so that you can imagine this is E plus, E minus, And in this case, for the middle part, we have E plus on this direction, E minus also on this direction. So they add up together. And actually, the magnitude should be the same. But for the left-hand side part, E plus, this is E plus, and E minus point to the right side, so that they cancel, which means that E should be 0 here. And then for the right side, E plus point to the right side, and then E minus, and then E minus point to the left side, E minus, point to the right side. So they cancel each other, which means that E equals to 0 at the left side and right side. Only the E exists in the middle part. And actually they sum up together. So which means that it should be 2 sigma 1, 2 sigma 1, 2 epsilon naught. Actually, if we put them together, all the positive charge will go to the inner plane, and then all the negative charge will also go to the inner plane, so that the surface charge density will be double. For that case, half of the charge will be on the left side, half of the charge will be on the right side. So that in this case, E plus will double to this case. E minus will also be double to this case. So finally, E would be this one add with this one. So that E would be E plus E minus. So this one and this one cancel. This one and this one cancel. This one and this one cancel. So when we add them together, we have 2 sigma 1 epsilon naught. And we redefine the final charge, surface charge density to be sigma rather than sigma 1. So that we define sigma to be the new surface charge density. So that finally, E would be sigma over epsilon naught. So it is, if we have parallel plate with excess charge, one is positive charge, one is negative charge, then there will be uniform E field between the parallel plate. Assume the plate is very large, and actually this is actually the capacitor. 电容。And you will learn more in chapter 25. So, any questions? So maybe I can call it a E plus prime, so that you don't mix up with the top one. So it should be with the prime, so that you don't mix up this one and this one, this one and this one. Okay, so no question. We have a sample problem. So here, portion of 2 large parallel non-conducting plates, each with a fixed uniform charge on one side. The magnitude of the surface charge density, sigma plus, and then sigma minus, which is not the same amount. So for the negative charge plate, find the electric field to the left of the plate, to the left, between, and to the right. So for non-conducting, it means there will not be induced charge, or for this case, the charge will be attracted to the inner surface. But for non-conducting plate, which means that the charge are not free to move. So in this case, we have a sigma E plus equals to sigma plus over epsilon naught, 2 epsilon naught, because there will be E field on both sides. Okay, E plus, and then for E minus, it will point to the plate. So this one point to the left, this one point to the left, this one point to the right, this one point to the right, and then this one point to the right, point to the right, point to the left, because for the E minus, it will point to this plate. For E plus, it will start from the plate and then pointing outside. So we plug in the numbers, which is 6.8 times 10 to the minus 6, and then over 2 times 8.85 times 10 to minus 12, which is 3.84 times 10 to 10 to the 5th power. So E minus is sigma minus over 2 epsilon naught, which is 4.3 times 10 to the minus 6 over 2 times 8.85 times 10 to the minus 12, which is 2.43 times 10 to the 5th Newton per Coulomb. So it is E plus E minus. And for A, we would like to calculate the E point to the left side, E on the left side, E to the left of the plate. So EL would be E plus minus E minus. So it would be 3.84 minus 2.43 times 10 to the 5th power, which is 1.14 times 10 to the 5th Newton per Coulomb, and then it should be pointed to the left side. So for part B, which is EB would be so we have a right side. So we have E plus plus E minus. So it would be 3.84 plus 2.43 times 10 to the 5th power equals 6.27 times 10 to the 5th power Newton per Coulomb, and then point to the right side. For part C, E out. So we have a plus minus minus. So E plus minus E minus. So which is actually this value, 1.14 times 10 to the 5th power Newton per Coulomb. And actually this is point to the right side. So any questions? Okay. Yeah, finish this one. So next, so I just mentioned the shell theorem. So yeah, I already mentioned it in the example. So if we have a shell with a charge, no matter positive or negative, then if it is inside the shell, then we can draw any Gaussian surface like S1 which share the same center, and then as long as there are no enclosed charge, then the E should be 0. For surface S1. And for the outside, as long as the charge, all the charge, so it will feel like, suppose for surface charge, surface S2, then if R is larger than capital R is the radius of the if the charge of the charge sphere. then E will be something like this. So nothing special. So the next case is applying Gauss law for spherical symmetry. So now suppose we have a non-conducting sphere, and now we assume all the charge are distributed uniformly. All the charge are distributed uniformly. The Gaussian surface, and this is the charge density, the volume charge density. So rho is the volume charge density. Rho. So for the outside the sphere, we can just simply draw the Gaussian surface outside, and then the Q enclosed is nothing but Q. So we get the similar expression for R is larger or equal to capital R. But for the inside the sphere, we need to really calculate the charge density. So the charge density will be the total amount of charge divided by the total volume of the sphere. So which is 4/3 pi R cube. 4/3 pi R cube. And the Q enclosed will be 4/3 pi small R cube. So actually pi and pi can be cancelled. And then 4/3 can also be cancelled. So Q enclosed is like this, which is proportional to R cube. Proportional to R cube. So actually we can apply the Gauss law so that on the left side we have E times the area, E times the surface area, which is 4 pi R. Suppose we have a Gaussian surface with a radius to be small r, and then the Q enclosed is this one. So we can plug it here, and then finally we can cancel R squared with this one. So and R remain. So we have R times Q over R cube, and then this way. So in high school, maybe when you learn this stuff, you need to really remember why it would be like R and then R cube. Of course, after the dimension cancel, then there will be R square, something like that, meter square in the denominator. But actually, why it would be linearly proportional? Why the E field will be linear proportional to the radius? It should be explained by the Gauss law. It should be explained by the Gauss law. So Gauss law can easily derive this expression. So in this case, suppose we have a non-conducting sphere with a uniform distributed charge, which has a radius r. So for the outside part, E will be like this, which is nothing special. But for the inside part, it is linear increase. So they join here. So for this part, it is proportional to R, but for this part, it is proportional to 1 over R squared. So far, any questions? Okay. So we have some additional example. We have volume charge density of a solid non-conducting sphere. Radius r, and then the charge density is like this, which is not uniform, which is related to r, related to small r. For this case, the rho is a constant. Rho is a constant. Rho is a constant here. Here, rho for here, rho is a function of small r, which is maybe I can call this number rho s times r over r. So this is rho s. And then what is the sphere? What is the sphere's total charge? What is the sphere's total charge? So actually we can calculate the total charge. We can calculate the total charge by this integral rho dv for the sphere. For the sphere. So actually, rho is a function of r, so that we can just write rho s times r over capital R. So this is rho. And what is dv? What is dv? This is a sphere. This is a sphere. So we can use the spherical coordinate. SPHE, spherical coordinate, 球坐标球坐标。So for spherical coordinate, we have r, theta, and phi. We have r, theta, and phi. So dv should be r squared sine theta, dr d theta d phi. Dr d theta d phi. Should be something like this. Actually, you learned it in calculus class. Actually, you learned this in calculus class. So r squared sine theta, dr d theta d phi. So what is the upper and lower and upper limits for the integral? So actually for the r, for dr, it should be from 0 to capital R. And for theta, it should be from 0 to pi. From 0 to pi. Yeah. And then for phi, it should be from 0 to 2 pi. 0 to 2 pi. So actually, you can check the spherical coordinate on maybe Wikipedia. You'll know that. So suppose you have a point here. R is the distance from this point to the origin. And then you can project it on the xy plane, and then this is Z. So when you project this point to the xy plane, this angle will be phi. And then this angle will be theta. So theta will be ranging from 0 to pi or minus 2 pi to pi. Minus 2 pi to pi. Let me see. I think, yeah, 0 to pi. Should be 0 to pi. And then for the phi, it should be 0 to 2 pi for a cycle. So in this case, phi s is a constant. Phi s is a constant. R is also a constant. So we have a 0 to R, and then we have this one R squared dr, so that we have a R cube dr, and then we have rho s, we have R, so we have these two, and then next we have sine theta d theta, and then this one, so that we have 0 to pi sine theta d theta, and then still remains is this d phi, and then we don't have phi inside, so we will only have 0 to 2 pi d phi. So in this case, we have a rho s over r, and then this one is r to the 4th power over 4, and then substitute r and capital R and 0, and then subtract them. So we have r to the 4th power over 4. And then for this one, it should be minus cosine theta, and then substitute 0 and pi in it, and then subtract them. It will be 2. And then for this one, you just integrating 1 from 0 to 2 pi, so it will be 2 pi. So the final expression will be like 4, 2, 2 will be cancelled. So that it will be a very nice expression like pi rho s times r to the 3rd power, because r and r to the 4th power cancel one of the order. So like this. So actually we can substitute the number. So pi times 35.4 times 10 to the 12th pico is 10 to the minus 12. R is 0.056 cube, 5.6 centimeter. So Q would be 1.95 femtocoulomb. Femto is 10 to the minus 15. So this is the charge on this non-conducting sphere. So next we have part B. For part B, what is the E field at r equals to 0? So you can simply imagine E would be nothing but 0. It would be nothing but 0 because you have a charge sphere, and then if you have a very very tiny Gaussian surface, then it encloses almost nothing. And as r equals to 0, E should be 0. E should be 0 at r equals to 0. So for part C, suppose we for part C we will need to calculate the r from r at capital R over 3, so that we actually really need to repeat this Q enclosed a bit. But here we have rho s over capital R, and then we have a r cube dr from maybe r prime, and then from 0 to r over 3, because suppose we have a conducting sphere with the radius capital R over 3, but however here we only consider here a point here. This one is R over 3, R equals to R over 3. So this is R. So we only consider the charge inside. So the remaining part is actually the same: 0 to pi psi theta d theta, 0 to 2 pi d phi. So in this case, we have a rho s over r, and then this one is r over 3 to the 4th power over 4 times 2 pi. So the expression will be like rho S R over 36 epsilon naught. So not this one, not this one yet. This one should be let me see, rho S R, rho S R, and then R to the third power, and then over 81, over 81. Let me see. Over 81, over 81. Yeah, over 81. So we have epsilon naught times E times 4 pi R square, which is R over 3 quantity square, equals to Q enclosed rho S R cube over 81. So this is the Gauss law. So finally we have a E should be rho S times R over 36 epsilon naught. 36 epsilon naught. I think I forgot a pi there. Pi, because we have pi here. 36 pi, yeah. Okay. So we can substitute all the number. We have a 35.4 times 10 to the minus 12 power, and then minus 0.056 over 36 pi times 8.85 times 10 to the minus 12. So E will be 6.22 times 10 to the minus 3 minus third power Newton per Coulomb. So this is for part C. Part C. Wow. Okay, so yeah, so we have still something to go. So here we have part D. For part D, it asks you about the E at R equals to capital R. So actually, we already know that Q equals to pi rho S R cube, which is actually 1.95 femtocoulomb in part A. So this one will be equals to epsilon naught E 4 pi R square. So actually this one will be or maybe I can keep this to be small r, first. Suppose R is larger or equal to capital R. Larger or capital R. So we have E should be equals to rho S R cube, rho S R cube over 4 epsilon naught R square. So this is for R is larger or equal to R. So actually we can just plug in R equals to capital R so that it becomes rho S capital R over 4 epsilon naught. And then we can plug in the value. It is like 35.4 times 10 to the minus 12 times 0.056 over 4 times 8.85 times 10 to the minus 12. So E would be 5.60 times 10 to the minus 2 Newton per Coulomb. So this is for part D. Or actually for here, we may try to somehow rewrite it like epsilon naught E 4 pi R square, and then equals to rho S. Actually, we can still keep this one. Keep this one to be like here. Here we have a rho R. We have R. We also have R to the fourth power. R to the fourth power. So that we have something like R to the fourth power over R, something like this. And then actually we can calculate Q enclosed R equals to capital R over 3, and then we can still get this one. So we have rho S R to the fourth power over capital R. So that we have E should be equal to rho S over 4 pi epsilon naught, and then R square over R. Let me see. R square. R to the fourth. This is R. Let me see. 4 pi R square. R cube. Rho S times R. R square over R. So this is for R is smaller or equal to capital R. So this is the expression for the E field inside the sphere. So for part E, we can really draw it out. So here we have this expression, E equals to rho S R cube. Rho S R cube over 4 epsilon naught R square. 4 epsilon naught R square. For R is larger or equal to R. And then for here we have Pi. Here we have a pi. Here we have a pi. Here we have a pi. So that we don't have a pi. We don't have a. Yeah, we have a pi here. So we have a pi here. Okay. We have a pi here. So that we don't have pi here. Okay, we don't have pi here. We don't have pi here. So actually we also have pi here. So we don't have pi here. So it should be epsilon naught. It should be like this. And yeah. So actually this is the expression rho s over 4 epsilon naught. E equals rho s over 4 epsilon naught, and then we have R square over capital R. R square over capital R, for R is smaller or equal to R. So here we can draw it out. So we have R here. So we have R here. So this one is proportional to R square. Proportional to R square. So this is proportional to R square. This one. Or maybe I can draw this part in red color. So this is like this, proportional to R square. And then for that part, it is inverse proportional to R square. So this is proportional to 1 over R square. And this point is 5.6. Oh, this point is 5.6 times 10 to the minus 2 Newton per Coulomb. This is E. 5.6 centimeter. So we managed to draw this figure out after some calculations. So any questions so far?